So now I wanted to shift gears and start talking about really the technical aspects of mounting these facade systems on buildings and what the issues might be with that. And obviously there's a whole lot of engineering going on here. And the intent of this part of the process is not to make you an engineer, but to help to sensitize you to all of the forces that are there and what things need to be put into consideration. And we're actually going to do a little bit of a deep dive into at least one of those calculations. So in the first illustration we have, obviously the facade has to be hung to support the gravity load or the weight of the facade itself, which in many cases is nothing trivial when you think about this terracotta weighing hundreds of pounds. So a cassette could easily weigh 1,000 pounds with its glass and its other elements. Those are still relatively light loads compared to cantilevering, compared to what the floor systems are designed to support, and maybe one of the simpler parts of the engineering. Some of the more complex parts of the engineering, though, I'll go all the way to the right-hand side, and we talk about the idea of the facade, and I'm hiding that, and I'll just move away for a second. The racking of the panel, either to the building swaying or racking under seismic load or wind sway, or also the deflection of the floor itself from having loads placed on it, and imagining that all of our panels are clipped on and supported by that floor. So if that floor deflects, it has an impact on what's happening with how the panels are hung on each other. And then the center one, the one we're going to focus on because it's kind of the it's germane to kind of our analysis because of a couple of things that are going on. One is, in the general idea, it's wind loads on that facade. And why wind loads are interesting is because it can be easily evaluated with some techniques that we know. And wind is climate related, and there are changes in the amount and strength of wind systems. And so this is probably one of the more dynamic and changing aspects of the way we design facades. And then the third reason about that is that in order to resist that facade from deflecting, we know that we're going to have to resist that with the mullion of the window. And the depth of that will determine whether it is strong enough to support it. And as architects and designers, we're concerned with the aesthetics and the amount of material that's used in that facade in order to resist this load. So with that in mind, and I'll go in the right direction, I want to make sure that we're kind of clear on this idea of what's happening with this wall deflection. So I have an illustration above this. This is from the building codes. And it talks about allowable deflections for curtain wall framing for stud walls. We're actually doing glaze systems with aluminum. So this is but this is a good introduction to the idea of thinking about deflection. And and we talk about deflection, we talk about L over some number. And if we were to talk, let's say for L over 240, it is the length of the beam in inches. So if we had a beam that was 240 inches long, and we had an L over 240 deflection, that means that the beam under its load, maximum calculated load, would deflect 1 inch. And as the number goes up, the deflection goes down. So at 480, the deflection would be 1/2 of an inch. So a higher number, L over 720, is a higher, stiffer type of assembly. So I said that this was a easier way to think about, or this idea of looking at wind loads was one of the things that was easiest for us to evaluate. And this is kind of an explanation why my thinking goes that way. So here we have the beige is a representation of that facade panel, or cassette as I like to call it. Arrows are the uniformly distributed wind load, and the two arrows coming back are the supports, the force that needs to resist that wind load. And we know that that connection of the panel system to the floor is kind of a pin connection. We've looked at that connector as a hook over that, so we know that it's rotating, it's free, it's not constrained, it's not a rigid one. So we can easily think of conceptually rotating this panel system to a way that we're more familiar with thinking about analyzing it as a simply supported beam. And then it is a simply supported beam with a uniformly distributed load. And we can find mathematical formulas to help us calculate the deflection of that. One of the nuances to the discussion of this L over is that when we're talking about wall deflections, we actually can change that to an H to be more clear. We're talking about the span height when we're talking about a wall, so it might be H over 360 instead of L over 360. I want to take just a minute to kind of qualify our work. we're not really here to engineer this. We're trying to get some kind of, I guess, fundamental understanding about the kinds of analysis that our engineers do for us, and a little handle on the effects of climate change on our building systems, and the effect of the shape of our members in resisting these kind of loads. But we're not engineering it. We're leaving some things out of our analysis. For instance, that member that is going to resist that wind load, we're not dealing with buckling or twisting of it. We're not dealing with the connection of the glass to it to know that if it is a fixed connection and whether there's rotation in the beam or not. So we're just doing some very fundamental or initial calculations to get a sense of the magnitude of the elements that we need to construct to create a wall with the performance we want. So I've included a couple of slides here. They're all hyperlinked to a Steel Institute's discussion about facade systems, and it has some interesting details and notes in it. I think that this is a really good graphic. It kind of shows you similar ideas that we've just discussed. You can see the blue arrows and the orange arrow at the top, the gravity load with the gray arrow, the idea of how those loads are resisted on the floor deck. It brings up this nuance that what happens at that joint between the two panels. If it is a spandrel and going down like that, where does that panel then join up with relationship to the clip system? And is that if that's a flexible connection, you'll notice the forced arrows are going both in the same direction, meaning that that clip can rotate out of position. And then how do we resist that force of it rotating? More than we will deal with in the course, but just what, or even in our project, but the kind of things that engineers are thinking about. The other thing is this idea of negative pressures on the building. So we think about wind load as pushing against the glass surface, but for every force there's another force like equal and opposite. And so at some point there is a vacuum created in a high wind speed, which would create a suction pressure to pull the panel from the building in the opposite direction. So the forces have to be considered in both directions. In our case, we simplify it and just carry it in one direction as a wind load from the exterior. And this is a good illustration. Once again, these are hyperlinked to the specific YouTube video that goes into the engineering of it. But you can see the illustration of the idea of floor deflection, and then how that would cause the kind of movements within the panels. And the length of the panel now becomes, in this case, is illustrated to becoming more critical. Long panels with any kind of floor deflection will create a more accentuated kind of racking of the panels, so to speak. So we're going to actually do, and to really close up this first part of it, I'm going to describe what we're going to do, and then in the next video clip, I'm going to go through the specifics of this creating of a spreadsheet. I want to give some credit to John Arshorn from Cornell. He was a structural instructor there in the School of Architecture, and he really kind of got me stimulated with this idea of using spreadsheets to do calculations for students. And this helps to eliminate a lot of issues by getting the units correct, doing relatively in-depth calculations, and becoming comfortable with them. So we're going to look at creating these kind of spreadsheets, and we're going to need to start assembling the data that's needed for that. So the first idea about our coming up with this deflection spreadsheet is to find the right formula. So we went back to building structures from your Structures 1 class. We know we can find a formula for the deflection of a beam, which is defined by I'm illustrating up in that red box that I selected. And I actually took a screen clip of that and then pasted it right directly into the spreadsheet. So I had that as reference material while I will be building the formulas for the spreadsheet. We need to figure out how to calculate the wind loads on a panel, which is actually turns out to be a relatively simple thing to do. But we need to understand, and in kind of understanding this, there's a little base knowledge that comes along with it that's really important. So the wind pressure, the amount of force that's created by the wind on a surface, and this is in relatively simple conditions. We're not talking about the wind blowing off the sides of it, but just basically air pressure loaded upon a continuous flat surface. We can calculate that pressure as being a coefficient number of 0.00256 times the velocity, in this case it's in miles per hour, squared. And what's really important in this calculation, and we're going to use this calculation in the spreadsheet, is that square the velocity. So if we go from 30, which would be 30 times 30, which would be 900, I believe. If we go to 40, we're not going up, we're actually, let me pick simpler numbers for the illustration. If we were going from 3 miles an hour, and that was squared, that would be 9. If we go to 4 miles an hour, it's now 16. So even though we've only gone up 1 mile an hour because it's squared, the impacts on the pressure of the panel system become very much more significant. And that's why at hurricane levels, these forces have immense amounts of destructive powers within them. And so on this idea of wind loading, and why I think that dealing with facades and wind loading is just an interesting subject for architects to deal with, is with climate change, we're starting to see hurricanes and wind speeds that are typically at becoming now at the highest levels and exceeding expected wind speeds. So we're needing to start to adjust our code accordingly. So just a few years back with Hurricane Laura, we were looking at hurricane level 4, category 4 hurricanes striking, which has just an immense amount of power compared to the milder storms. And so I think this will be continuing to be an important subject in the design of all kinds of assemblies that we as architects make. And then I just want to finish up that there are other pieces of software available that can really help us do these kind of analysis of wind forces onto buildings. In this case, it's using Rhino and Grasshopper. And up to this point, there was no way to actually introduce these into coursework. But in the future, we'll be able to, by using Rhino and Revit software plugin, we'll be able to use these advanced tools to do analysis right inside of our modeling software. So enough on wind load. We have to figure out how to take that wind load now and move it into something meaningful for our analysis, that beam. So the white vertical element is that mullion. And our way of thinking about that tributary area is not the cassette itself, because then we'd have to divide that over 2 beams, but to think about that tributary as being that shared load from the two cassettes together, which is exactly the same 5-foot width span. In this case, of a 15-foot high cassette. And this is just a simple way we'll deal with tributary loads, and you should be familiar with this because it's really exactly as you would deal with it if you were calculating floor loads for beam deflection for structures. Critical in that formula, as you'll see, is this identifying the moment of inertia. And so the way we're going to do it is you could use calculators that you put in the geometry and it gave you back. But in this case, I'm going to show you how you can, off the internet, grab tables and then put those on your spreadsheet, figure out a section property that you like, a shape of a beam, find out its properties, put that number in, and now you can analyze the deflection according to how tall it is, how wide the panel is, and what wind speed you're trying to design for. The other inflection point about deflection is the material that we use. So if we use an aluminum alloy, we get we have a modulus of elasticity that's a certain value, and this should be familiar back with what you learned in structures. And with steel, a much stiffer element, it has a higher modulus of elasticity. So, or Young's modulus, should I say. So we have those two numbers. We could either imagine this thing being made out of steel or being made out of aluminum, or if you really wanted to stretch things, you could actually look at it being timber and find the Young's modulus for timber. So we're going to put that all together in a spreadsheet so that we can do some graphic representations, and we can start to think about how we can do some analysis of that to determine how large or deep our extrusion should be for our facade element mullion. And this is just a close-up of that formula. In the next video, I'll step through opening up a Google Docs and show you what is created in all of that in order to build up your own calculating spreadsheet.